then, so here's our first one. We have the modulus of x equals 5. Okay, and so what we're doing is we're trying to say what are the possible values of x that would satisfy this statement. If the modulus of x is 5, then x is plus or minus 5. All right, that you can put positive 5 in. The modulus of positive 5 is 5, and the modulus of negative 5 is 5. Okay, so our answer, the modulus of x equals 5, x is then positive or negative 5. All right, that's A. On to B. We have the modulus of 3x take 2 equals 7. Okay, so what we do is we get rid of the modulus and we make it equal to plus or minus 7. And then we solve through to get x by itself. All right, so we will add 2 to both sides. Let's break it up into two circumstances. We've got 3x take 2 equals 7, or 3x take 2 equals minus 7. So we're considering the positive case and the negative case. We're going to have two possible solutions. We'll solve this. And then over here, we have two values of x that satisfy the original statement that we began with. Okay. Now we do have some properties, modulus above, that we can apply, but for now let's just stick with the algebra. What we're going to do is multiply both sides by this modulus denominator to get rid of it. So we'll have the modulus of x take 3 equals 4 times the modulus of 2x plus 1. Alright, so I'm moving that term up there. And then we'll put the plus or minus here, I reckon. So we've got plus or minus x take 3 equals 4 times 2x plus 1. Alright, so we need to consider both the positive case and the negative case. So let's do the positive case here. We'll do the positive case first, and then we'll find the negative case. So the positive case occurs when we have positive x take 3 equals 4 times 2x plus 1. And so we're just going to solve that equation. So, I mean, we love algebra, don't we? 8x plus 4. Get the x's on one side, the numbers on the other. So we'll have 7x, and we'll take 4 from both sides, minus 7. X is minus 1. Alright, so I'm hoping we're pretty comfortable with solving linear equations. Alright, so here, what did I do? I took x from both sides, and take away 4 from both sides, divide both sides by 7. Good, so that's the positive case. Let's consider the negative case. So the negative case occurs when we have minus x plus 3 equals 4 times 2x plus 1. Equals 8x plus 4. Plus x to both sides. Take 4 from both sides. How do we end up with, actually, how do we end up being plus? That's what's going on here. Because we have the negative of x take 3 makes it negative x plus 3. And then when we take 4 from both sides, we'll have minus 1. Everybody happy with that? Excellent. Good, okay, so they start pretty okay, don't they? So let's do, we've got 2x equals the modulus of x. Let's let you go, I'll pause for a little bit, I'll let you guys have a go at this one. Alright, so I'll expect you how to do that. So you can put the plus or minus on either side here, it doesn't matter. I'll put a solution up at the moment. But I'm also going to bring up Desmos for some of the later questions.
Plus or minus 2x. What year is that? Yeah.
Doesn't matter what side we put plus or minus on. good, which is really good.
That's not. No. Take the
And I might actually, this next one will span across two boards because there's a fair bit involved in this next question. So the next one that we have, and Seth, you might remember getting the feature there. This popped up in the previous exercise, and I said it's going to pop up when we do
Oh, yeah.
3F. Now we can see this one's a little bit different because the absolute value does not apply to the whole of both sides. We have this +1 sitting over here. And so what we need to do is we need to break this down into separate domains. So if we remember the definition of absolute value, okay, let's define both functions given a domain first. So for the first one here, we're going to have 3x take 3, the modulus of it. It's going to equal 3x take 3, provided 3x take 3 is positive. And it's going to equal negative 3x take 3, provided 3x take 3 is negative. That's just the definition of absolute value, right? Now we can process these inequalities a little bit. This would give us 3x being greater than 3 and x being greater than 1. And same with this one if we solve it, x being less than 1. Okay, so we have the modulus of 3x take 3 is going to be this function for values of x larger than or equal to 1, and it's going to be this function for values less than. That's the definition of absolute value. Okay? Then we'll do the same for the equation on the right hand side. Is your hand up?
Oh, yeah.
Sorry.
Does the sign of the inequality not change if it's divided by
It's
something?
if we divide by a negative.
Right.
Yep. So it's only if we multiply or divide by a negative that it will flip. Good. Okay, so that's 3x take 3, and then we have modulus of x plus 1. Well, this will be x plus 1 for x is greater than or equal to 0, and it will be minus x plus 1 for x is less than 0. Okay, so we've got a couple of domains here to consider, right? So I'm going to draw just an x-axis, a number line, and we're considering domains. We've got 0, and we've got 1, and values larger than 1. So I'm just going to do this a bit like a sine diagram, isn't it? So if we're looking at values less than 0, we've got to say which equation are we using. So for values less than 0, on the left-hand side, which of these, and I'll rub this part out there to simplify our notation a little bit, which of these corresponds with x being less than 0? It's this one. If x is less than 1, all right, then that's also going to satisfy x being less than 0. X being less than 0 will also satisfy x being less than 1. So we're going to use the negative case for the left-hand side, and for the right-hand side of the equation, we will also use the negative case because that is when x is less than 0. All right. Then if we consider the circumstance between 0 and 1, okay, between 0 and 1, well, I'm still using this equation, okay, because between 0 and 1, it has to be the negative case. It has to satisfy that domain, x being less than 1. So for the left-hand side of the equation, that's the one we're going to use. But for the right-hand side of the equation, if it's between 0 and 1, well, this is the domain that satisfies that condition. And so this is going to be the equation that we use. All right, and then for the last set, if we have x is larger than 1, we're going to have the 3x take 3 on the left-hand side, and we're going to have the x plus 1 on the right-hand side. Okay, so that means we've got 3 different equations that we're going to solve here. We've got an equation for when the domain is less than 1. We've got an equation for when the domain is between 0 and 1. And we have an equation for when the domain is larger than 1. All right, so do you see, depending on where we are looking at the functions or the equations, it dictates what function we're using. Okay, so do you see how we've tamed this wild thing into 3 separate equations? And so for x being less than 1, I can just look at my number line, and this is the equation I'm solving, when this equation equals this one. So we'll write that out. We have minus 3x plus 1 equals minus x plus 1. All right, we'll just go ahead and solve that. Plus 3x to both sides, and take 1, and here we get sorry, that should be a 3. That should be minus 3x take 3, shouldn't it? And so that makes that line. That's going to change anything else with it. Minus 3x take 3, minus 3x plus 3. And we take 1 from both sides, we'll have positive 2. And so we'll have x is positive 1. Okay, so I've written the wrong function here. Make sure you get it right there. Okay, now, this is a solution to the equation, but it's not a solution that exists to our, it's a mathematical solution, but it's not a graphical solution. And let's explain why. If we consider the domain is x is less than 1. That should say x is less than 0. Oh, I'm really sorry. We've got x being less than 0, x being between 0 and 1, and x being larger than 1. Okay, x is less than 0, but our solution is x is 1. This does not exist in this domain, so that means this is not a solution. All right, when we look between 0 and 1, these are the functions we're using, right? Minus 3x take 3. Equals x plus 1. So again, plus 3x to both sides, and take 1 to both sides. That'll make that plus. Take 1 equals that 2, and so we get half. Okay, x is half. Now, this solution exists inside this domain, therefore this is one of the solutions to our problem here. Okay? This solution does not exist inside the constraint we've provided, so that's not solution. Okay, let's consider the last circumstance, which is when we have 3x take 3 equals x plus 1. Alright, take x from both sides, add 3 to both sides. X equals 2. That does satisfy the constraint as well, therefore this is a solution. So we can do an algebraic process, right, by breaking it down into its components. But let's bring out for you some Desmos, and we'll graph these. So we'll break it Vivi out as well. And you guys can graph it on your graphics calculator too, if you remember how to bring up the absolute value. So I'll just go to Desmos, PRC 6. And the code is 8260. Desmos. Show me Desmos. So, how do I bring up absolute value here? Modulus of 3x take 3. All right, that would be the first graph. Well, that's your y1. And the other graph we're considering is the modulus of x plus 1. Okay, so we can graph both of those. Just a reminder, to bring up absolute value, it's option, calc, and then numeric, and then absolute. Pretty sure that's right. Calc's not. It's just that option numeric. Option numeric. Okay, there's no calc step involved. Option, numeric, absolute. Very good. All right, so I've graphed both of these, and if we the solution, so when is this equation going to equal this one? Well, we can solve it algebraically, or we can graph both and g-solve the point of intersection, and we can see half, okay, half is a solution, and notice that solution occurs between x is 0 and x is 1, doesn't it? That's the domain over which we're saying that solution must occur. And the other solution, x is 2. And what's not a solution? X is 1. Okay, it's not a solution, doesn't occur over the appropriate domain. Very good. So that's how we can use, we've done how to graph these already. So that's a skill done. We can find a graphical solution by graphing them either using technology or manually, and we can perform this algebraic process as well. For the remainder of the problems, let's look at how we can use our calculator. So for the remainder of the problems, we've got F. Find x such that the modulus of x is greater than 1. Okay, so here we have an inequality. Now what I'm going to do is I'm going to sketch the function of the modulus of x, and I'm going to sketch the function. So I've sketched the left-hand side, and I'm going to sketch the right-hand side as well. What's on the right-hand side? Y equals 1. Okay, so you can see it up there. This is what it looks like. I'm going to draw it here. So this is the graph of the modulus of x. This is the graph of y equals 1. Okay, intersection here and here. And our question is, when is the modulus of x larger than 1? When is the modulus of x higher than it? And so it's here, okay, we can see the modulus of x line is higher than the line y equals 1, and we can see it's here. We can g-solve those points of intersection, 1 and 1, minus 1 and 1. All right, so I'll list those both there so that we can make our statement. So for values of x larger than 1, the modulus of x is larger than 1. And for values of x less than minus 1, okay, less than that x value, the modulus of x is larger than 1. Okay, so we're just graphing left-hand side, graphing right-hand side, making a statement. Okay, let's do g, which is the modulus of x take 2 being less than 5. Now, by the way, you can still perform an algebraic process for this as well. It's just when you multiply or divide by a negative, you switch the direction of the inequality. So we have modulus of x take 2 and y equals 5. So I've graphed the left-hand side, I've graphed the right-hand side. This is what it looks like. Okay, let's get those points of intersection. I've got x is minus 3 and x is 7. All right, I won't sketch it again so I can make the statement. So it's like this kind of thing. And we've got the median here, x is minus 3 and x is positive 7. This is the line y equals 5. This is the line the modulus of x take 2. Now the question is, when is modulus of x take 2 less than 5? Well, it's over this interval, isn't it? Over this interval here, the modulus of x take 2 line is below the line y equals 5, and that occurs between x is minus 3 and x is minus 7. And I think the question says less than or equal to, doesn't it? Yep. The question says less than or equal to, so that means including those points because it's equal at those points. So our answer for this one, minus 3, less than or equal to x, less than 7. We're obtaining that from the graph, both of those. And then for our very last one, we have the modulus of x squared take 2x. And that's for y1, and then for y2, we have the function 2x plus 1. All right, so that's what our curve looks like. I'll sketch it up on this one. Cool curve. Okay, that's the modulus of x squared take 2x. And And then we just have the line 2x plus 1. It's going like that kind of thing. And so they're intersecting here and here. And the question is, when is the quadratic, the modulus of the quadratic, larger than the line? So the quadratic is this curve, and it's going to be larger than the line for values of x less than this one. And what's that value of x? We'll just g solve, it's going to be an irrational solution. We've got minus 0.236, that's the x value where they meet here. And the x value where they meet over here, 4.236. Alright, and so to answer the question, the quadratic is larger when x is larger than 4.236 and x is less than negative 0.236. Okay, very good. Alright, so there, the algebra is lots of fun. You can use your calculator to support you, but that's how we can find solutions to absolute value equations. So let's spend, I think,